Hello, we've got a past paper question, AQA past paper question on the halogens. It's taken from a year 2 past paper, it's year 1 content. So here's the first part of the question. If you want to pause it, take a look and have a go. Okay, so before I get into talking about the specific answer to this question, it's worthwhile comparing the reactivity of the halogens and also the halides. So when halogens react, they gain electrons and become halides. So the halogens are reduced, and so therefore halogens can behave as oxidizing agents. The electronegativity of the halogens decreases down the group. You should know the definition of the term electronegativity. The ability of an atom to draw a pair of electrons towards itself in a covalent bond. Because the electronegativity decreases down the group, the reactivity of halogens decreases down the group, and therefore the oxidizing power of the halogens decreases down the group. Now it's important at this stage to remind ourselves that halogens are very different from halides. They kind of do the opposite when they're reacting. So let's turn our focus to halides now rather than halogens. So when halides react, they sometimes lose electrons, and if they lose electrons and how many electrons they lose, this is about how powerful they are as reducing agents. So halides can be reducing agents, and the reducing power of the halides increases down the group. Now for AQA, what you need to be able to do is compare chloride, fluoride and iodide in terms of the reducing power or reducing potential in the reactions with concentrated sulfuric acid, and that's what we've got here. So for the first part of the question, we need to give an equation, and there's really no getting around the fact that this is just knowledge driven, content driven. You have to know the balanced equation. Chloride ions are not powerful enough in terms of the reducing ability to be themselves oxidized. So it stays as chloride on both sides there. So this is not a redox reaction. You should be aware that it will make initially the NaHSO4, that it will make the hydrogen sulfate ionic substance there rather than the sulfate. You would have got the marks for writing Na2SO4, but that is more correct. So Cl- is not a powerful enough reducing agent for this to be a redox reaction. What's happened to the sulfuric acid? Well, on the left hand side there we've got H2SO4, and on the right hand side 1 proton less is gone to HSO4-, so the sulfuric acid is a proton donor. Another way of putting that is that the sulfuric acid is a Bronsted-Lowry acid. Okay, so here's the next part of the question, and you can see we've turned our attention from sodium chloride to sodium bromide. So it's a comparison of how the bromide reacts compared to how the chloride reacts. So we need to give the equation, an observation, another observation, and the role of the sulfuric acid. So there's the balanced equation. Again, it's worthwhile knowing these off by heart. Well, we can see that the bromide has gone to bromine on the right hand side there. I've shown the bromine as being Br2 gas. I understand that it's Br2 liquid at room temperature and pressure, but initially you will see brown fumes because the bromine will be quite hot, and as a consequence it will be seen as brown fumes. Okay, so there's the brown fumes of bromine there, but yeah, I understand if you put that as a liquid. It is a redox. The bromide has itself been oxidized. It's gone from an oxidation state of -1 to 0. So what has been reduced? The sulfur in the sulfuric acid is reduced. You can work out the oxidation states, but we've got a little bit of oxidation states work to do in the next question, so I'll leave that for you to have a go at. So the sulfuric acid is an oxidizing agent. The sulfur in the sulfuric acid is reduced, so the sulfuric acid is an oxidizing agent. Now, we weren't asked in this question about the reaction with sodium iodide, but just for completeness, you should be aware of the full reaction and corresponding balanced equation. There's a balanced equation, and what we can see with the iodide, it's not only gone to iodine, but which it has, but the sulfur has not only gone to SO2, it's indeed gone to H2S. So the sulfur has gone through an even bigger change in oxidation states. Sometimes it's also possible to get the solid sulfur, which would be seen as maybe a yellow solid, but that's a balanced equation that would suffice if you were asked for the reaction with sodium iodide. Okay, so the next part of the question is an oxidation states question. So see if you can work out what the oxidation states are of the different elements in that equation. Not only NaClO3 and NaCl, not just the chlorine though. See if you can work out the oxidation states for all of them. So if you're not aware of the rules, here's an opportunity to kind of refresh your memory on those. Combined group 1 and 2 metals have an oxidation state of +1 and +2 respectively. Combined hydrogen has got an oxidation state of +1 apart from in hydrides, so metal hydrides for example. Combined oxygen is usually -2 apart from in peroxides, in which case it's -1. By combined, I mean hydrogen in the elemental hydrogen gas H2 has got an oxidation state of 0, same with oxygen. In elemental oxygen it's got an oxidation state of 0. Oxidation states of atoms in elements is always 0, as I just gave the examples there of hydrogen and oxygen. And the sum of the oxidation states is equal to the overall charge on the compound or ion. So there's the rules and the guides for assigning oxidation states. That should give you enough to work out the oxidation states of each of these atoms. And there we have it. Just another note to be aware of: if you're going to annotate the equation, make sure that you annotate with the oxidation states rather than the total positive or negative charge. And also, I know it's only a slight difference, but if we take an example for the chlorine in NaClO3, the oxidation state is +5, not 5+. It's slightly different. So it would be, for example, 2- would be a charge, whereas -2 would be the oxidation state. So now just to address the question really, oxidation state of chlorine in NaClO3 is +5. Oxidation state of chlorine in NaCl is -1. So a 1-mark question here, and we could get straight to it, but if it were worth more marks it would require more explanation, so I've given extra explanation. Oxidation state of chlorine in Cl2 is 0. Then we have the information from the previous question in terms of the oxidation state for chlorine in the other two compounds there. So chlorine is both oxidized and reduced. It is disproportionated. So disproportionation reaction is one in which the same element is both oxidized and reduced, as chlorine is in this case. So final part of the question now, and we've got some tests for ions work to do. So good opportunity to read the information there, and I think you just from the information in question, you can work out any relevant equations, identify the species. So the information has been abridged here, and the specific questions are given for you to attempt. Okay, so let's see how you got on. Here are a few prompts. Which anions form a precipitate with silver? Which anion bubbles with protons or in the presence of an acid? And can you recall the colours of the silver halide precipitates? So the anions that form a precipitate with silver are the halides, with the exception of silver fluoride, but silver chloride, silver bromide and silver iodide. The other anion that forms a precipitate with silver, which is relevant to this situation, is carbonate. So silver carbonate is also a solid, an insoluble solid. Carbonate will also form carbon dioxide or effervesce or fizz or bubble with H pluses. The colours of the silver halide precipitates, and there's an extra clue here in the question: white for silver chloride, cream for silver bromide and yellow for silver iodide. And the solubility in aqueous and concentrated ammonia also helps you to deduce more clearly which silver halide precipitate you have. Silver chloride will dissolve in aqueous dilute ammonia. Silver bromide will not, but it will dissolve in aqueous concentrated ammonia, and silver iodide will not dissolve in concentrated ammonia solution. So from that we can deduce that D, E and F must be silver bromide because it doesn't dissolve when you add the HNO3. E must be the Ag2CO3 because that does dissolve, that does react with the H pluses in the nitric acid. And F, there must be the gas which is formed when we add the nitric acid to the silver carbonate. So now we're asked to develop the ionic equations. This is already quite a lengthy video and I can give more information on developing ionic equations, but a couple of rules to remember. Anything which is aqueous and ionic you can split into its ions on both the left hand side and the right hand side of the equation. Anything that's solid you cannot split up into its constituent ions, and anything that is covalent, well, doesn't contain ions, so you cannot split those things up. So we've got a couple of examples of ionic equations on this answer here. So the ionic equation showing the formation of E. We know that we have silver ions and carbonate ions, and we know that we're making silver carbonate. Now, because that's a solid, we can't split the silver carbonate up into its ions. It has to be balanced, so we've got 2 silvers on the left-hand side and 2 silvers on the right-hand side. And I like to include the balanced equations because it helps us to identify why certain things can be split up and why certain things can't, and it's also linked to the observations. So that's clearly showing that a precipitate is formed. What about some of the other ionic equations? Well, if we take the silver and the bromide, that forms a precipitate of silver bromide. So we've got the aqueous silver and the aqueous bromide, making a solid silver bromide. And what about the formation of the gas? Well, the H pluses and the CO3 2 minuses, they come together to make the CO2 gas, so that is linked to the bubbles, and also water. And as we can see there, water is a liquid, so it's not ionic, it's covalent. The carbon dioxide is also covalent, so we can't split those up into their ions. So the final part of the question now is about converting D into G. AgBr, solid, plus ammonia makes something called a complex ion. Now this is on the year 2 specification, but there's no harm in learning about it now. The square brackets there represent that the AgNH32 is what we call a complex. The NH3 is acting as a ligand, an electron per donor. And the whole thing has got a positive charge, and we can see there that it's also formed the bromide, so it's kind of the NH3s have replaced the bromine. There's the balancing number, If you've done aldehydes and ketones or even alcohols yet, you should be familiar with the name for the complex that has been formed and the associated test. So we would use that, we would make it in the laboratory out of usually silver nitrate and ammonia, and that's known as Toland reagents. And Toland reagent can be used to test for the presence of an aldehyde as a silver mirror is formed, whereas ketones, because they will not undergo further oxidation, they will not give a silver mirror.